What's a chemical bond? That's the question we're going to ask today. How and why does it form? What's in it? And what determines its strength? To do this, we're going to have to think like a scientist, not a game show contestant. Right? In game shows, everything is right or wrong, black or white. But if you want to think like a scientist, then you're going to have to Google less and think more. It's not just about facts. Scientists use facts, sure, but they think in terms of models, principles, and theories, and how empirical data fits or doesn't fit these models. So let's think of a chemical bond. Often we draw it like a stick, right? So let's think of that. The chemical bond is a stick. How can we model that? Well, turns out if we have a couple of masses, the two atoms, and they're stuck together by a stick of length r, then we can very easily model how that stick rotates, right? It'll rotate through space. You'll get a rotational vector J perpendicular to the bond axis there, and that model is known as the rigid rotor. And we can model the energy states of a rigid rotor and how they would be distributed, go up in higher and higher energy, the more rotational energy you put into it. And we could use spectroscopy then. Spectroscopy is light matter interactions, the absorption of light when you go between states. We can use spectroscopy then to interrogate the rotational structure. And indeed, rotational spectroscopy out in the radio wave area, radio astronomy, is the primary way that we identify molecules in space. So if you look out into the Crab Nebula, we can identify molecules by thinking of molecules as being bound with a stick between their atoms. And indeed, more than 99% of all molecules identified in space have been identified using rotational spectroscopy. So that's pretty good. We can identify most molecules in space, but real molecules vibrate, right? So a stick can't be the right model, right? The stick model must be wrong. But no, think like a scientist. The model's not wrong, it's incomplete. We need to develop it further, right? Something is holding together the atoms in the molecule, but it can stretch and compress. It's not rigid. So let's think of the bond as a spring. And we have a model that describes how a perfect spring works. And that's known as the harmonic oscillator model. And the frequency of these vibrations would be related to the chemical bond strength and the atomic masses. And again, we can use physics then to calculate what the energy level structure of a harmonic oscillator would be. Shown over here. Nice even spacing between the levels, and then the sides of the potential will go up to infinity. We can use that model to look at how atoms in a molecule move. And what we'll find is that when we get a molecule such as benzene that we have here, that different atomic motions have different frequencies, different energies associated with them, and that if we looked at the interaction of infrared light with the molecule, we would see peaks at different spaces. The spectroscopy would allow us to interrogate the bonds in the molecule, and that's one of the primary means of identifying what is in the bonds in a molecule, which atoms are available. The simple harmonic oscillator model was also used by Planck back in 1900 to solve one of the great mysteries of the time, known as the ultraviolet catastrophe. That is the spectrum of light that comes from a heated body. All objects at any finite temperature radiate with a characteristic spectrum that depends on the temperature of the object. And the Planck distribution here, very simple formula. Planck used the harmonic oscillator model along with the idea that vibrations are quantized to describe this distribution. And indeed, that ushered in the quantum revolution in the description of matter. But molecules dissociate, so we need to tweak our harmonic oscillator model and introduce what's known as the Morse oscillator. A real bond, if you start to stretch the bond, it will fall apart. If you put energy into the bond, you can get it to dissociate, and we need a model that shows that. Here, we've shown that with a curve known as the Morse oscillator. And it emphasizes the point when you start out here, when molecules are very far apart, they're not interacting. As you bring them together and form a bond, energy is released. Always remember, bonds release energy when they form, not when they break. So what's the spring made of? What's the bond made of? Well, in our system, we're going to have nuclei and electrons. The electrons are running around in space. The nuclei are made up of protons and neutrons. And it was in 1919 that Langmuir was the first to suggest that a covalent bond is made up by sharing electrons. We should be able to model that. We know what the total energy of the system should be. It should be kinetic energy plus potential energy. Let's say the nuclei are fixed because they're so heavy and the electrons running around. Then we just have to worry about the kinetic energy of the electron and then the electrostatics. Unlike charges attract, like charges repel. So the nuclei repel each other. The electron is attracted to the nucleus. Here we'll just take the simplest molecule of all, H2+, and we should be able to calculate things easily. Just one problem. That electrostatic interaction means that electron should just spiral into the nucleus, and this is not going to be a stable system. All the way as it spirals in, it's just going to emit radiation. And that's not true. Molecules are stable. So, oh no, everything we know about physics must be wrong. That's how the game show contestant thinks. But a scientist says, no, our model is incomplete. Let's think about it more deeply. We need to balance forces. The forces have to be zero at equilibrium. How are we going to do this? We're going to minimize repulsions, electrostatics. We're going to maximize the electrostatic attractions. And we need to minimize the kinetic energy of the electron. That's what we had in before. But now we have to do that quantum mechanically. And that's what brought us to this amazing decade of where Schrödinger said, the electron is a wave, and introduced his equation. He didn't know what was wiggling in the wave, but the wave was required to describe the system. Heisenberg, on the other hand, said, no, the electron is a matrix, and there's this uncertainty in its position and energy if we're trying to specify those at the same time. Good, we're getting closer to a description, but there was this odd thing that only two electrons seemed to be able to go into a region of space at the same time. Pauli made an essential observation that in order to put the electrons in the right order, you had to believe that there was some other angular momentum associated with them. Let's call it spin, and exclusively when those electrons come together in an orbital, one's got to be pointing up and one's got to be pointing down. That didn't really make a whole lot of sense until Dirac solved Schrödinger's equations in 4 dimensions, not 3, treating them relativistically, with time also added as a dimension, not just the 3 spatial dimensions. And this showed that 4 quantum numbers were required to specify not only the energy of the electron, but also which orbital it occupied in space. But we weren't really sure what this wave function was until the Born interpretation of the wave function, which was that the wave function itself is a probability amplitude. The wave function squared represents a probability density, that is the region of space occupied by the electron. That was a really nice thing that he figured out what the wave function was all about, but we know what he's really famous for. What he's really famous for, of course, is his granddaughter, Olivia Newton-John, multi-million selling pop star, and his postdoc. Indeed, Robert Oppenheimer was a postdoc with Max Born, and the two working together came up with the Born-Oppenheimer approximation, which is required to calculate those potential energy curves like the one I showed you earlier. Okay, so we can describe orbitals around atoms in particular, and we can describe the simplest of molecules, H2+, but not much else with the mathematics that was developed up to this point. And it took Pauling and valence bond theory to really give us a description of bonding in both, not only in diatomics, but in polyatomic molecules. And there, what he talked about was bonding being, okay, we're going to combine atomic orbitals to form bonds. And sometimes we'll have to do hybridization, combine more than two orbitals in order to get the geometry right. And when we put these atomic orbitals together, they're going to be bonding and anti-bonding combinations. The bonding combinations are constructive interference, which enhances electron density between nuclei, whereas anti-bonding combinations, those are destructive interference that reduce the electron density in the internuclear region. All wave functions always are made by taking a spatial part and a spin part, which we need because we got to pair these electrons, one up, one down in spin, so that the Pauli exclusion principle is followed. This was great. We now have a set of rules that describe a bond. Unfortunately, as pointed out by Dirac, mathematically, we just couldn't describe these in an accurate way using these rules. And that's where it remained for a long time, until the work of John Popel in the 60s and 70s, which developed molecular orbital theory, or as he called it, the theoretical chemistry model. He built on the work of others such as Slater and Hartree, Fock, Rutan, and Boys. And the idea is, let's give up on these atomic orbitals. Atomic orbitals are great for describing atoms, but it's a molecular potential that the electrons are in now. We got to worry about their energy and their angular momentum, but we need functions that will describe them in the molecule. So let's use something easy to integrate, Gaussian orbitals, and we're going to put those together in a basis set. We'll call it a set of functions that we're going to add together to construct the molecular orbitals of the system. And he did this in a way that took the wave equation and turned it into a minimization problem. In fact, we use the matrices of Heisenberg in this method to minimize the energy of the system and find the right coefficients that add these basis functions together to make the molecular orbitals. He also introduced the use of perturbation theory to work on electron correlation. And what these methods really gave us then was a way to visualize bond formation. So we could build upon our molecule. We don't have to think of a bond just as a stretchy stick. Yeah, that's a nice way to write it down, but let's think about bond formation in HCl and use the methods of developed by Popel and others to really visualize bond formation. Now we could look at total electron density. That egg-shaped thing doesn't look much like a bond anymore, does it? It is where the electrons are, and if we calculated then the electrostatic potential, we would see, yes, the chlorine is more electronegative, it pulls more electrons toward it, so the electrostatic potential is greater on the chlorine side of the molecule than the hydrogen side, but it still doesn't look much like a bond, right? For what the bond really looks like, we need to look at the bonding molecular orbital, which is represented here for the HCl molecule. In fact, we can look at the development of a bond as a function of distance, the separation between the hydrogen and the chlorine. As we bring them closer together, the orbitals are going to overlap. The functions that describe the electrons that go into the bond are going to overlap. They're going to interfere constructively and really form that bond between the hydrogen and the chlorine. So one last question is, what determines the strength of the bond? And this turns out to be a very subtle question. It depends on the distribution of electrons in space, how they're distributed relative to each other and to the nuclei. So the shape and distance between charged particles is really important. We also have to look at spin and angular momentum. And in that distribution, one of the properties that's really important are the nodes that are introduced, the places where the wave function goes to zero. What the molecule is trying to do is to minimize its total energy. It's trying to minimize potential energy. That's all the electrostatics in the system. It's trying to also minimize the kinetic energy increase, because it turns out that the electron kinetic energy always increases upon bond formation. And it's only really recently that this can be described in a quantitative way. And there's a very insightful paper just came out from Martin Head Gordon and others. And they talk about the things that go into quantitative bond formation. You got to minimize the potential energy. That term is fairly well known from the electrostatics. The more subtle term is this minimization of the kinetic energy. First, the kinetic energy drops, and then it always increases when a bond is formed. And a number of factors go into that: node-induced confinement and orbital contraction, as well as the relative electronegativities of the species that introduce polarization into the bond. Using these concepts now, we can really describe bond formation and what a chemical bond is. And a chemical bond is the constructive interference between electron wave functions that leads to an enhancement of electron density between the nuclei to lower the energy of the system.